Hey everybody, it's Mr. G. Welcome back to Tech 101. Today what we're going to be covering is topics from lesson number 1. First things we're going to be doing is looking at components. So things like, what is a resistor? What's a capacitor? What's an inductor? What's a transformer? And then what we're going to be looking at is things that do with number systems. So we're going to be looking at scientific notation, we're going to be looking at engineering notation, and we're going to be looking at what's known as a prefix. So that's what we're going to be looking at today. So some basic components and then number systems, or things to do with numbering systems and doing our math. So let's take a look at some of the components. The first one and the most basic component is the resistor. So the idea of introducing a few components to you is so that you have an idea of what you're going to be doing throughout this course and the components you're going to be using. And if I happen to use this in a sentence and say resistor or whatever, you happen to know what I'm talking about. So a resistor, the schematic symbol. So schematic symbol is the electronic symbol you'll find in electronic diagrams. Looks like that. The unit of measurement is the ohm, and the symbol for ohm is the Greek letter omega. So the job of a resistor is to limit current flow in a circuit. And again, over the next few weeks, we're going to really get into resistors and what they are and what they're made of and how they work and their values and all that kind of stuff. But for now, a resistor, that's the symbol. The unit is the ohm, and the symbol for the ohm is the Greek letter omega. And the job of a resistor is to limit the flow of current. Next is a capacitor. A capacitor, its electronic symbol, it has a few of them. The unit of measurement is the farad. F for farad. Basically, a capacitor in the realm that we're dealing with is a small storage device. So it stores an electrical charge. So that's what a capacitor does. An inductor. Its symbol looks like a coil, because that's what an inductor is. It's a coil. The unit is the Henry. H for Henry. The inductor we're going to be studying in other courses. So most of Tech 101 is based on resistors. We introduce the capacitor at the end of the course. Inductors, you're going to look at that in your next set of courses. Then we have the transformer. Now everybody knows what a transformer is. It's a robot in disguise. Optimus Prime, we've got Megatron. and all of the others, you know, all the Autobots and Decepticons. And there's a big war that was brewing years ago over Cybertron, and we ended up with a bunch of different movies. But in this particular case, the Transformer is a device. Its symbol kind of looks like this. And its device is to take one level of voltage and change it to another level of voltage. And again, you're going to do a bunch of studying on different transformers and how they work, and then take it from there. So all of the different transformers like Optimus Prime and Bumblebee, etc. So basic components: resistor, capacitor, inductor, transformer. Then we've got some measuring tools. So measuring tools. There are three main elements, if you will, to electricity. The first one is voltage. And we'll talk more about voltage, but basically voltage is the energy, the potential difference that causes electricity to flow. So when you look at a battery, so if you take a battery and you have a positive terminal and a negative terminal of a battery, the potential difference between those 2 points is a voltage. If you were to measure voltage, you would use a voltmeter. So I just happen to have a multifunction meter here. So this will actually measure voltage. We have AC and DC voltage, and we'll talk more about that as the course gets on. But we would put the voltmeter in DC voltage. If we wanted to measure a battery, we would turn it on and we would put our lead to where it says voltage. And then if we were to take a battery, so I just grabbed this old, what's supposed to be a 9-volt battery, and I am going to clip my leads onto the battery. There it is. And the battery is 9.13 volts. Okay, so that's a measure of voltage. The next element is current. So current is basically a measurement or a movement of electrons. So as electricity flows through a wire, that is what's known as current. So if you think about it, if we had a wire and we used some energy from our battery, we could get electricity to move through that wire. The movement of that electricity, that is a measurement of current. So if we wanted to, we could actually measure current. Now I'm going to show you the last one. The last one is a measurement of resistance. Resistance, remember, is the opposition to current flow. So it restricts or reduces or controls current flow. So what I'm going to do is really quick, I'm going to set up for you a little circuit, and we will measure current in a resistance. So here is a resistor. These are the ones that you have in your kit. So what I'm going to do is I'm going to use that little battery that I had just brought out. So there's my little 9-volt battery. And I'm going to get a couple of little jumper leads. I got one. Oh. And there is two. So basically what we're going to do is we are going to take a measurement of current in a circuit. So I need to set this up to measure current. Current is measured in amps down at the bottom. So I'm going to set it up to measure current. So I have a 9-volt battery. I'm going to force the electrons to move through the resistor. And then return to the battery. So there is a measurement of current. So that happens to be what's known as 6.63 milliamps of current. So the three main components that build up circuits as far as elements go, we've got voltage, current, and resistance. So the resistance is the opposition to current flow. The voltage is the potential energy that causes electricity to flow. Voltage is measured in volts, current is measured in amps, and from before, resistance is measured in ohms. So if I look at the circuit that I had just built for you, you could look at it like this. Here is the battery, the positive terminal. Here is the negative terminal. We went up into the meter, out of the meter, into the resistor, and then returned. So that is how we actually counted the electrons that were flowing. We put the meter in the line. So all of the electrons had to go through the meter to make their way through the loop. So the job of the resistor is to control or limit the amount of electrons that are moving. The job of the meter is to count them and give us a measurement in amps. So this was 6.63, I think it was, milliamps. So what does this all mean? So that leads us into the next topic. So stay tuned, we'll be right back. All right, so we're back. Numbers. In this course, there are three different ways of expressing a value that we need to cover. The first one you've probably already become familiar with, which is in scientific notation. Scientific notation is a way of expressing a number and taking that number and using it as a multiplication factor of 10. So as an example, I will take the number 2,470. So the number 2,470 represented in scientific notation looks like this. 2.47 times 10 to the 3. That's what we know as scientific notation. Scientific notation has one significant digit before the decimal point, and then everything else is represented as a factor of 10. So when I look at this, this is actually 2470 is 2.47 times 10 to the 3, so that's times 10 to the 3 is 10 times 10 times 10, that is 1,000. So that works out to be 2.47 times 1,000, which is 2.47 thousand, or 2,470. So scientific notation is a way of representing a number in a particular form. That particular form takes into account one digit before the decimal, then the decimal, then the remaining digits, and then a multiplication factor that is based on powers of 10. So another example would be 271,420. In scientific notation, this works out to be 2.7142 times 10 to the what? Well, basically, we go like this. Where is the decimal point? It is there. So if I take my original number and I move the decimal point 1, 2, 3, 4, 5 spots, this becomes 10 to the 5. So here's our original number. This is the scientific notation of that particular number. What if I did 0.2146? As far as the scientific notation goes, again, I need one number to the left of the decimal, so that becomes 2.146 times 10 to the something. So now, instead of moving the decimal point, so going from here and we're moving the decimal point this way, we're actually moving the decimal point that way. So that actually is one spot to the right, so that becomes one spot minus. So to the minus 10. So 10 to the minus 1. So scientific notation, again, its job is to represent any number in a particular form. And that form is one number, so one significant number, before the decimal, and then use the times 10 to the whatever to express the rest of the number. So scientific notation says one digit before, and then use the expression 10 to the whatever to represent the rest. So then, what is engineering notation? So scientific notation is one significant digit before the decimal, and then representing the rest of the number as a power of 10, if you will. What is engineering notation? Well, engineering notation is actually a specific set of scientific type notation numbers. Engineering notation uses a very specific set of powers. So we have the base unit. So the base unit is actually going to be 10 to the power of 0. So we know that anything to the power of 0 is 1. So what we're going to do is we take any number and multiply it by 10 to the power of 0, and it becomes that same number. So that's the base. Engineering notation uses a specific set of these numbers. The base is 10 to the 0. Then we have 10 to the 3, 10 to the 6, 10 to the 9, and 10 to the 12. On the opposite side, we have 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, and 10 to the minus 12. So what they represent, if the base is 1, this represents 1,000. So multiply by 1,000. This represents multiplied by 1,000,000, 1,000,000,000, and 1,000,000,000,000. On the other side, it's 1 1,000th, 1 1,000,000th, 1 1,000,000,000th, and 1 trillionth. So, engineering notation uses a special set, and it's powers of 3. So 3, 6, 9, 12, minus 3, minus 6, minus 9, minus 12. So those are all the ones that you're responsible for in this particular class. So if I had a number that looked like this, 4,321. If I wanted to represent that as a scientific, it would look like this. 4.321 times 10 to the 3. That's scientific notation. If I want to represent the same number in engineering notation, we do have a 10 to the power of 3 right here. So that would be the same number in engineering notation. But what if we have this one? 52010. In scientific notation, that works out to be 5.201 times 10 to the 1, 2, 3, 4. Scientific notation. But in engineering notation, there is no 10 to the 4th. We can only use these values that are given in engineering notation. So, we would have to change that. And that would become, for engineering notation, 52.01 times 10 to the 3. So in scientific notation, it's one significant value before the decimal point and any power of 10. In engineering notation, it is any values before the decimal, but we need to specifically use these values or multiplications of 10. So hopefully you see the difference. Scientific notation, one decimal point. Okay, so one digit before the decimal point. And any value of power of 10. Engineering notation, we have any values we want before the decimal, but we must use a power of 10 that is one of these. So whether it be 10 to the 12, 9, 6, 3, 10 to the 0, minus 3, minus 6, minus 9, and minus 12. Now you might ask, well, what's the difference? Why do we use one instead of the other? Well, engineering notation is based around the way we talk. Scientific notation is based around mathematics. So what I mean by that is that for each of these powers, there's actually a word that is used to describe them. So most people are familiar with them already. So I'll just label them all here. 10 to the 3, which is 1,000, is known as a kilo. So if you know how far a kilometer is, so if the base is the meter, so the base is the meter, a kilometer is 1,000 meters. This one here, 10 to the 6, that is mega. Ten to the 9 is giga. 10 to the 12, tera. So when we're talking about computers and we say gigabytes, so gigabytes. So it's actually 10 to the 9th bytes. Megahertz, 10 to the 6th hertz. Terabytes, we got terabyte drives now. So being able to store huge amounts of data, 10 to the 12th, tera. On the other side, when we get smaller, 1/1000th is called a milli. 10 to the 6th, so that's 1/1,000,000th, is called a micro. 1/1 billionth is called a nano. And 10 to the 12th, 1 trillionth is called a pico. So the symbols for each of these looks like this. K, capital M, capital G, capital T. Small m, Greek letter mu, small n, small p. So engineering notation has a direct correlation with the way that we talk, not mathematics. Okay? So it's manipulating scientific notation expressions and picking a few of them so that we can actually give them names and when we're speaking about it. So just a couple of minutes ago, I did a measurement for you. .63 milliamps. So what that is 6.63 times 10 to the minus 3 amps. So this is engineering notation. This is what we call a prefix. So in the English language, a prefix is a small word that you put at the beginning of another word to change the meaning. So if you have the word meter, so we all know how big a meter is. A kilometer is 1,000 meters. The word kilo at the beginning, so kilo at the beginning of the word meter is 1,000 meters. Megameter is 1,000,000 meters. So you take the word mega and you put it at the beginning of the word meter and it changes the value. That is what's known as a prefix. So, what we have is scientific notation. So scientific notation, a number, one number before the decimal, any numbers after, multiplied by any power of 10. That is scientific notation. Engineering notation is taking any of those and adjusting them so that we are only using certain powers of 10. And again, it's multiples of 3. So 10 to the 3, 10 to the 6, 10 to the 9, 10 to the 12. 10 to the minus 3, 10 to the minus 6, 10 to the minus 9, 10 to the minus 12. That is engineering notation. Engineering notation goes hand in hand with prefixes. So tera, giga, mega, kilo, milli, micro, nano, pico. Those are the prefixes. So that is our speaking language, how we can describe a value or give a particular value an expression of being really large or really, really small inside our language without actually doing mathematics. So engineering notation combines scientific notation with the way that we actually speak in prefixes. Okay, so when we're doing a representation in math, it's much easier to say 5.2 kilo ohms, okay, than it is to represent saying 5,200 ohms. So there is a way of speaking that makes things easier, and then it correlates to doing the math with the actual numbers, the scientific notation type. So we've got factors of 10. So in engineering notation, we are using specific factors of 10, and we assign each one of them a name. So throughout this course and throughout the rest of your study and your rest of your career, you will be using these engineering notations. You will be using these prefixes all the time in your discussions, in your calculations, and so forth. So again, when we looked at, we took a meter reading and we got something that was 6.63 milliamps. That milli is a prefix and it describes the actual value, so the size of the actual value. So, today what we've done, we've talked about the basic components, resistors and capacitors and inductors and transformers, and we have looked at the basic elements of electronics, which is voltage, current, and resistance. And we have also done the numbering systems. So we've looked at scientific notation, engineering notation, and prefixes. So in our textbook, Principles of Electric Circuits, Conventional Current Flow, Floyd and Buckla, if you look at quantities and units, chapter 1. So chapter 1 will talk all about the things that we talked about. Scientific notation, engineering notation, prefixes, how to do basic calculations, how to convert from one form to another. Okay, so in your lesson notes in week number 1, you've got reading material from the textbook. There's examples and things. So let's just take one simple example and say, if I had 4,121 kiloohms, what is that value in mega ohms? So I have 4,121 kiloohms. How many mega ohms do I have? So first you have to ask yourself, which is bigger, a kilo or a mega? Okay, so mega is bigger. So if I had 1 kilo ohm, if mega's value is bigger, I would have a value of less than 1 mega ohm. We know that the value of here is 10 to the 3, and the value here is 10 to the 6th. So 4121 times 10 to the 3 must equal something 10 to the 6th. Now, we can go ahead and put this into base units. So that means this is 4,121,000. That's our base number. So one way to do it is to say, okay, that's our base unit. We want it in mega, which is 10 to the 6th. Take the decimal point, move it 6. 1, 2, 3, 4, 5, 6. So that becomes 4.121 times 10 to the 6th. So 4,121 kilo is the same as 4.121 mega. So you could put it into base units and then work from there, but that's a little bit of an extra step. If you know that the difference between 10 to the 3, which is kilo, and 10 to the 6, which is mega, you know that the difference is only 3 movements of a decimal. So to go from 10 to the 3 to 10 to the 6 is a movement of 3 decimal points. So when we're going from a big number here and we're going to a smaller number, we're moving the decimal point 1, 2, 3, 4.121. If we were going the opposite direction, so 52.4 mega ohms, how many kilo ohms is that? Again, we know that this is 10 to the 6th, this is 10 to the 3. So we know that if we have 52.4 mega ohms, we must have many more kilo ohms. So now we're going to move again the decimal point from 6 to 3 is moving it 3 points, but now we're moving it the other direction. So we got 52.4 and we're going to move it 1, 2, 3 spots. So this works out to be 52,400 kilo ohms. So that's basically how you simply convert in engineering notation and in prefixes from one to the other. There are many examples in the textbook. So take a look at what we've got in the textbook. Again, it's Principles of Electric Circuits, Floyd and Buckla, Chapter 1. I hope this helps. Stay safe, everybody, and we'll see you next time.